In this video, we want to take a look at three vector spaces that are associated with each matrix. So here we go. Given an M by N matrix A, we define the column space of A to be the span of the columns. All right, think of each column as a vector, and just take the span of those things, and that would be the column space. Likewise, given an M by N matrix, we define the row space to be the span of the row vectors. Right? Each row, consider as a vector, take all linear combinations, and you get what's called the row space. And given an M by N matrix A, we define the null space of A to be the solution space of AX equals 0. This one we've looked at before. We've proven that solution set of any homogeneous system is a subspace, right? Some things to notice here. I claim that the null space and the row space are subspaces of Rn, and the column space is a subspace of Rm. So first of all, let's see. The matrix is M by N, so M rows and N columns. Well, if it has M rows, that means every one of the column vectors has M entries in it. So the column vectors are elements of Rm. So if I take linear combinations of things in Rm, I get a subspace of Rm. That's the column space. The column space is a subspace of Rm. Likewise, this has n columns, and so every row vector has n things in it. If it's got n things in it, it's an element of Rn, and if you take linear combinations of things in Rn, you get a subspace of Rn. So the row space is a subspace of Rn. Likewise, the null space are the x's here that satisfy this equation. Well, in order to make this matrix multiplication make sense, A is M by N, so x has to be N by 1. And N by 1 means it's an element of Rn, and so we have a subspace of Rn. It's kind of interesting in that the row space, I think of writing the vectors, the rows as rows, right, horizontally. But the x's I would write vertically. But either way, you've got n things in a row, or you've got m things in this single column x here. So the null space and the row space are both in Rn. The column space is over in Rm. If A happens to be square, of course, then you're in the same space either way. So a few things here that relate these spaces to stuff we've already done. Theorem. The system AX equals B is consistent if and only if B is in the column space of A. So here's my proof. Just remembering how we do some things here. Right? To say AX equals B, X is this vector with n things in it, or it's a column matrix with n things in it. And how do you multiply a matrix times another matrix, particularly when the second one is just an n by 1 matrix? Well, I mean, there's different ways I think of it. One is that I look at the rows of A and dot them with this column. So the first entry would be the first row dotted with this column. The second entry would be the second row dotted with this column. But at the same time, what's happening is that the things in the first column of A are all getting multiplied by x1. Things in the second column of A are all getting multiplied by x2, and so on down the line. The nth column, everything in the nth column is getting multiplied by xn. And then those corresponding columns are being added together to create this single column that's the vector B here. And so essentially what we're doing here is we're taking a linear combination of the columns where the coefficients are whatever the x's are. So we say this is consistent if and only if B is in the column space. So if and only if means I got to prove it in both ways. If B is in the column space, there's a linear combination that adds up to B. Well, that linear combination, take those coefficients, put them in a vector here, call it x, and you've got a solution to that system. Likewise, if you have a solution to that system, you've got a bunch of x values here, a bunch of numbers which are assigned to x1 up to xn. You plug them in here as coefficients, and you've got a linear combination that adds up to B, because we know that this is a solution to that system. So AX is equal to B, and that's what we want. Okay. So when you're looking at the column space, you're essentially looking at this side over here, you're looking at the b's. You're saying, well, what things can we get when we do a times x? What are the b's? And that's the column space. The null space was what are the x's that make not this equation true, but when it's a homogeneous, when there's a 0 here, right? So the x's on a homogeneous system are telling you the null space. The row space, sorry, the null space of the x's, the column space are what b's you can get out of this. Right? So for instance here, I asked the question, is 1, 1, 1 in the column space of this matrix, 1, 4, 7, 2, 5, 8, 3, 6, 9. If you think of the column space, look at the columns, 1, 2, 3, 4, 5, 6, 7, 8, 9. It's one of my favorite matrices. So the question is this in the column space? That is, can this vector be written as a linear combination of those? Well, that's the same thing as asking, is this non-homogeneous system consistent? Does it have a solution? Well, I can figure that out by making an augmented matrix and putting it into, actually I did go all the way to reduced to echelon form here. And what I see is a whole bunch of zeros across the bottom, and I see a free variable. So not only is there a solution, but there's infinitely many solutions. And so definitely it is in the column space. And in particular, here's one way of doing it. I don't know why I have 2 parentheses there. Maybe if I just keep going, no one will even notice that it was there. But if we multiply this vector times minus a third and this vector times plus a third and add them together, you can see this would, like in the first place here, this would be 4 thirds minus a third, which is 3 thirds, which is 1. 5 thirds minus 2 thirds, 6 thirds minus 3 thirds. Anyway, we get 1, 1, 1. So yes, this is in the column space because this system has a solution. Very similar situation here. I'm going to take the same matrix, but I'm going to just ask a slightly different. Rather than 1, 1, 1, how about 1, 1, 2? Is that in the column space of this thing? Is there a way of taking linear combinations of the columns to add up to that? Well, try this one. Instead of 1, 1, 1 down here, I've got a 1, 1, 2. Get to, again, this is reduced to echelon form. But now there's a 1 right here, and so that bottom equation is 0 equals 1, which indicates to me that there are no solutions. And so no, this vector 1, 1, 2 is not in the column space of this matrix. It turns out that these 3 columns are linearly dependent. So you're really only looking at, when you say take the span of all three lie in the same plane, and so it's the same as just doing a span of 2 of them. And there are things in that plane which certainly are in the space, in the column space, but then there's things that are off. The point, take a vector that's not in that plane, and you can't take linear combinations of these things to get to that. And I've got one last theorem to end this video with. It is a theorem we've seen before, but I just want to rephrase it in terms of the language of null space and row space and that kind of stuff. And it says this: if you have one particular solution, so x0 is any particular solution to this non-homogeneous system, then the set of all solutions to that same system can be written as, or can be obtained by just adding this x0 to all the vectors in the null space of A. The theorem that we had before said that the set of all solutions look like x0 plus something from the solution set of the homogeneous system. Well, that's what the null space is, the solution set of the homogeneous system. So if you've got a basis for that null space, then all the linear combinations of that basis would be the whole null space. And so what you do is you just say take all the linear combinations, but then add the x0 on as well. So you got 1 times x0 plus any linear combination of the basis for the null space. Right? This is something we've already seen. It's just that now we have it in terms of the new notation.